Hello, my name is Xue Yang. I'm a data scientist at the Institute for Infocom Research, A-STAR, the Machine Intellection Department. My colleagues and I at the Machine Intellection Department work very closely with Singapore's public agencies and the different industry sectors to help them use AI to make good use of their data to create benefits for Singapore society and for their business. Today, I'm very glad to be here to share with you some of the techniques we use on a daily basis to make AI even better and sharper in tackling some of the most important daily applications. For a mission-oriented organization like A-STAR, we use AI to tackle real-world problems. We handle large amounts of different types of data, including sensory data, spatial temporal data, social network and service data, image, audio, and video data, text data, and structured data. From all different types of data, we use a comprehensive data preprocessing automation platform to clean them, integrate them, do feature engineering, and also do feature selections. With the preprocessed data, we'll be able to apply different AI and the data analytics methods, including supervised learning, unsupervised learning, semi-supervised learning, and the reinforcement learning. The supervised learning and unsupervised learning are the two most important methods that we use on a daily basis. Supervised learning deals with the problem where we give a very specific target for the machine learning to look for in a large amount of unlabeled database. And for unsupervised learning, we allow the machine learning algorithms to discover the pattern and the distribution of the data so that hopefully we can extract new insight and a new knowledge about the data that we look at. With all different methods, we'll be able to solve different problems from the industry. For example, for the engineering sector, we work with Singapore Airlines to help them predict the failures of their aircraft fleet so that we can reduce the overall downtime of their aircraft. For the urban development side, we work with Singapore public agencies to improve the efficiency of our bus systems and our traffic light systems. In healthcare, we work with different hospitals and pharmaceutical companies in Singapore to better improve the outcome of the patients and also to help them discover new drugs. And last but not least, for the digital service and the economy sector, we work with companies like KPMG to help them in their business as well. If you wish to know more about what we did for these companies, you can visit our booth to know more about the details of our projects. So let's first take a look at one of the most important category of machine learning, the supervised learning. The supervised learning deals with the problem where we give a very specific target to the machine learning algorithms and ask the machine learning to search through a large amount of unlabeled data points and to give us what are the similar ones to those we give as the training examples. For example, in this example, I will show you how the supervised learning works in the case of simply distinguishing cats from dogs images. Usually, to start the supervised learning process, the user will give machine learning some examples of dogs and the cats. They are what we call labeled data points. And the machine learning will, based on what we provide, learn the characteristics of what dog and the cat should look like. And then based on that, the machine learning will derive what we call a decision boundary. This is what basically distinguish what should be look like a dog and what should be look like a cat based on the machine learning's understanding. And another very important concept in supervised learning is what we call a margin. Margin represents the confidence of the machine learning in their predictions. If a data point is fall within what we call above the margin, that means the machine learning is very confident that the new data point belongs to a cat or belongs to a dog. But if, on the other hand, the new data point falls within the margin, that means the confidence level is low. So based on this, the machine learning algorithms will scan through the unlabeled data points and rearrange them based on their distance, based on their confidence, whether they look like a dog or whether they look like a cat. And some of them will be labeled with high confidence and be classified as dog and cats accordingly. But some will be fall within the decision margin. Those are cases where the machine learning algorithms are not very confident. So in this way, we are able to use machine learning algorithms to help us identify from large amount of unlabeled data points what are the examples that look like a dog and what are the examples that look like a cat. On the other hand, for unsupervised learning problems, we use the same pool of data points, but we treat them using a different approach. In this case, we do not give machine learning algorithm a typical example of cat or dog, but instead we ask the machine learning to identify the patterns, like what are similar objects among the data points. For example, we can define a similarity matrix, and based on that matrix, the machine learning algorithms will be able to group similar objects together. For example, in this case, the cats and dogs that look alike will be grouped together. And if we further relax this what we call the distance between the objects, then we can further merge smaller groups of data points. And we can keep doing that until all the data points belong to one single cluster. And one very important use of unsupervised learning in real-world application is to identify anomalies in the database. For example, if we set a very stringent clustering threshold, then we will be able to see that there are 3 clusters in the amount of 7 data points, and there's one outlier that does not belong to any of the clusters. But if we further adjust this boundary or threshold, we can merge more data points together, and we can have 2 clusters or 3 clusters, depending on the distance we use as the cutoff threshold for the clustering. So we have seen what supervised learning and unsupervised learning can do. Supervised learning help us look for similar data points as the ones we give to the machine learning algorithms, where unsupervised learning help us discover the new patterns and the relative distance among the data points in a database. But there are challenges in both the supervised learning and unsupervised learning methods. First of all, for the supervised learning method, there can be a lot of what we call insufficient or imbalanced training data. So that means for a simple example of cat and dog classification problems, there are tons of different types of dogs and the cats that could be classified. But because of the limitation of manpower and other resources, we cannot tell machine learning every single type of cat and dog. So what we provide to the machine learning algorithms is usually a very small or even tiny subset of what are available in the real world. So that is what we call insufficient training data problem. And what is the imbalanced training data problem? So imbalanced training data problem is an even more common problem in the cases where, for example, we want to look for some anomalies in the data points or predict some rare events. So that means, for example, in a machine learning for aircraft health prediction problem, we will have a large amount of healthy cases. On the other hand, we will only have a handful of failure cases. And that creates the imbalance between the healthy cases and the failure cases. And this problem will cause our machine learning algorithms to bias towards the healthy cases and become inefficient in predicting or identifying the failure cases. So this is the most typical insufficient or imbalanced training data associated with the supervised learning methods. On the other hand, for the unsupervised learning methods, it has also its own problems. So usually when we deal with unsupervised learning problems, the very important concept is the distance, meaning how close the data points are between each other. So we can actually introduce a lot of more dimensions to describe a subject or describe a data point. For example, just talking about cats and dog problem, we can actually introduce a lot of different attributes about cats and dogs. For example, like the color of their furs, their cries, and the way they walk. So there are a lot of different attributes we can introduce. In other ways, we can always put the data points in a much higher dimensional space. So that is what we call a curse of dimensionality problem. The curse of dimensionality refers to the situation when we project a data point into a much higher dimensional space, and the data become a lot more sparse among each other, so that when we consider the distance between data points, it becomes a very ineffective way to describe how close or how far away the data points are between themselves. So I will give one simple example to describe what does this mean. For example, if I'm in a new planet in a new universe and try to look for stars in this universe using a telescope, and I can control the radius of search of my telescope, and assume that the stars in this universe are all evenly distributed across the universe. And if this is a 1D universe, then when I extend my radius of search, I will have proportionally as many of stars identified as the radius that I go. But if it is in a higher dimensional space, for example, like if it is in a 2D space, if I increase my radius to half of the size, half of the dimension of the universe, I can only capture 1/4 of the total stars in the universe. And if we go even further, if this is a 3-dimensional space, when I use a telescope that can search at the radius of half of the universe, I can only capture 1/8 of the total stars in this universe. And this problem becomes even worse as we progressively increase the number of dimensions. For example, if we go to as high as 10-dimensional space, then when I use a telescope with a radius of 90% of the universe dimension, I can only capture as little as less than 40% of all the stars in this universe. But this number will rapidly increase when I further push my search radius from 90% to 100%. So this curse of dimensionality causes a problem for unsupervised learning in that it becomes very difficult for us or for machine learning algorithms to identify which data points are close to each other and which are very further apart. Because if you only use a smaller distance, then you see everybody are very far away from you. But when you reach a very high search distance, you will see that all the data points are very close to you. So that makes it very hard to find the right decision boundary that actually cut off between clusters of data points. So we have seen some challenges associated with supervised and unsupervised learning. So what are some techniques to tackle those challenges? So first of all, let's take a look at the supervised learning side. So for supervised learning, the unimbalanced data problem, there are a group of methods as what we call sampling method that can very effectively tackle the data imbalance problem. So today we'd like to introduce this particular method called synthetic minority oversampling technique, or SMOT. So let's first of all look at the oversampling method. So SMOTE belongs to a category of method called oversampling method. So oversampling method is the way that to increase the number of smaller data set in the data class. On the other hand, there's another category of method called undersampling method. The undersampling method, instead of increasing the number of minority class, they reduce the number of the majority class. So both undersampling and oversampling have their pros and cons. For the undersampling, the benefit is that it is usually a more straightforward method to implement. But the drawback is that the undersampling will reduce the original information in the dataset. On the other hand, the oversampling method can very well preserve the original information in the dataset. But how to oversample the minority class to ensure that the new synthetic data points also follow the same distribution as the original dataset is the key challenge in this. And the SMOTE is one such solution to perform the oversampling method. So let's take a look at how it is done. So let's first take a look at this picture here. So in this picture, we have two classes of data points, the majority green dots and the minority red dots. The objective of SMOTE or oversampling method is to improve the number of red dots by creating some new and synthetic data points that are similar to the original authentic red dots points. So first of all, SMOTE will identify each pair of the data points in the original class and along the lines between each pair of dots, SMOTE will randomly create some new data points. So this is a very basic format of SMOTE, using a very linear way of interpolating the data points between the original data class. Of course, there are other ways to do oversampling method. So in these 9 graphs, you can see that the first plot, the one on the upper left-hand side, is the original data set. This data set shows two classes. One is the majority red dots, and the other is the minority blue crosses. Using different oversampling method, we can all improve the representation of the minority class in the two classes dataset. But as you can see, like they are slightly different in terms of the end result between different methods. And even for SMOTE, there are different variations. And one particular useful trick that we usually use is to combine SMOTE with some other techniques. For example, kernel trick to improve the efficiency of oversampling for supervised learning problems. In the plot, for example, in the last two plots here, we can see that by combining the kernel method with SMOTE, we can actually very well separate the two classes of data points so that we can have a very easy job using a linear way to classify the two classes of data points. So kernel trick is actually one very useful tool in machine learning. It is about transforming some data from its original data space to a higher dimensional feature space. For example, on the left-hand side here are two classes of data points. These two classes of data points cannot be linearly separated. But through a nonlinear transformation that projects those data points into a higher dimensional feature space, we can actually identify a hyperplane that can perfectly classify the two classes of data points. So here is just to have a very quick summary. So we can actually tackle the data imbalance problem that are typically associated with supervised learning with oversampling method. And SMOTE is one common way to perform the oversampling. And we can also combine SMOTE with other techniques such as kernel transformation to improve the efficiency of oversampling for supervised learning problems. And now let's take a look at the unsupervised learning method. Just now we described the main problem with the unsupervised learning method is the high dimensionality of the data. And we know there's a category of methods that deals very well with high dimensional data, which is neural network. So let's take a look at a classical neural network architecture. Usually a neural network is used for classification purpose, meaning that given an object, for example, the image of a mushroom, we can design and train a neural network that analyzed the pattern of this picture and tell us that this is actually a mushroom. So the architecture of this type of neural network typically has an input layer which is equal to the size of the input space. For example, the number of pixels on this image. And then they will have several layers of hidden neurons. This is usually a much larger number of neurons than the input space. So each neuron will operate some very simple operations to analyze the input data from either the input layers or previous layers of hidden neurons. And at the end of the network, all the neurons will be put together into one single output layer that makes the final decision about whether this is a mushroom or it is not a mushroom. So actually, we can actually play with different architectures of the neural network, and they will give us very different results. And through the years of development, people identify this kind of architecture, which is called an autoencoder. So this is a very interesting architecture of neural network. You can see that it is completely symmetric. The left-hand side is exactly the same as the right-hand side, and very different than the traditional neural network that performs classification problems. In the autoencoder, the middle layers has a much smaller number of neurons. And this small number of neurons forms a compression layer. So the function of this compression layer is that they will force the whole neural network to compress the data or information from the input layer to a very small number of neurons. And the objective of this small compressed layer is to compress the data so that the key information of the object are preserved and can be used to reconstruct or decode the original data point. For example, when we train the autoencoder neural network, what I would do is to give the image of a mushroom at both the input and the output of my autoencoder. And essentially, I force the neural network to engage in data compression. So in the middle layer, I will be able to see a very low resolution image of the mushroom. So that will use smaller number of neurons to represent the key informations from the original image. And this autoencoder can actually help us solve the high dimensionality issues with the unsupervised learning. How does it do? So if you look at a normal, after we train an autoencoder to perform outlier detections, then we can first of all introduce a normal data, for example, another mushroom, into this autoencoder neural network. And at the other side of the neural network, I would be able to see a reconstructed image of the same mushroom, although they will not be exactly the same because through the compression, some information will be lost. But the overall on the high level, the construction error, that is the error between the original image and the new image, should be very low. And a low reconstruction error means that the original image actually belongs to the same type of data points that the autoencoder was trained on. Where on the other hand, if there's a new type of data that is very different or very say, in feature space, in a high distance away from original training data, that used to train the autoencoder network, for example, the image of a ghost, comes into this neural network, then we will, again, because the neural network is rigid, is a fixed network, so it will still perform the same operations. Each neuron will do the exact same operations, and at the end of the day, they will still create a reconstructed image of the original image. Then, because this whole neural network we use is trained based on the image of mushrooms, so it is actually tuned to reconstruct mushrooms. So although in the initial input side, we give him the image of a ghost, but at the output of the neural network, we will receive an image that still looks very like a mushroom. So the problem is that now when we compare the outcome against the income, then we will see that there's a very high reconstruction error. So by calculating the reconstruction error, essentially we are basically calculating the distance between the subjects and original training data, which is represented by this autoencoder network. So we have seen some of the most commonly used techniques to sharpen the supervised and unsupervised learning methods. And there are actually other ways to do it as well. For example, for the supervised learning method, we can actually ensemble different models together so that we can perform a better job in making the classifications. And for unsupervised learning method, instead of using the neural network-based anomaly detection method, we can also use other nonlinear dimension reduction method. For example, like PCA, or we can also use some nonlinear dimension reduction method like kernel PCA. And besides the supervised and the unsupervised learning, we can all actually combine the supervised and unsupervised learning together so that they can work together and perform a better classification and clustering at the same time. And some of the semi-supervised learning methods include active learning and co-training. So I hope through this presentation, you have some knowledge about our work and about the machine learning techniques we use on a daily basis to solve real-world problems. So if you have interest to know more about our projects, our work, and the research, please feel free to visit our virtual booth and also to visit our website. Thank you and goodbye.